Okay, here's our last topic of the chemistry unit. Who's excited? Who's a little sad that we're about to leave chemistry behind? Chemistry is awesome. So let's talk about chemical reactions and what exactly happens in terms of the energy changes associated with them. First of all, let's kind of rewind and remind ourselves what a chemical reaction even is. Here's an example of a chemical reaction. Hydrogen gas coming together with oxygen gas to form delicious, delicious water. And you should look at this and think, oh no, something is wrong. We have broken the law of conservation of mass. So remember, how do we fix that? Well, we've got to create a balanced chemical equation. We need to balance this. And I have satisfied the law of conservation of mass. 1, 2, 3, 4 hydrogen atoms. 1, 2, 3, 4 hydrogen atoms. 1, 2 oxygen atoms. 1, 2 oxygen atoms. That's a chemical reaction. And that's how we model it, using chemical equations, particle diagrams, etc. But what's actually going on here? Well, I start with different substances compared with what I end with. I started with hydrogen gas and oxygen gas, and I end with liquid water. That's amazing. I start with different substances, and I end with different substances. There's been a chemical change. The identity of the substances has changed, even though the total matter has stayed the same. Well, how did this occur? Well, I hope you remember that in order for this to occur, two things have to happen. The old chemical bonds have got to break. I have got to break apart those hydrogen atoms. I've got to break apart the oxygen atoms. Then the atoms can rearrange themselves, reshuffle themselves, reorganize themselves, and form new bonds. Two hydrogen atoms will bond with an oxygen atom. The other two hydrogen atoms will bond with the other oxygen atom to form these two brand new chemical compounds of water. So old bonds are broken and new bonds are formed, and whenever that happens, we have changes in energy. What happens energetically to the system? This is my system. What happens whenever old bonds are broken? Does the system require that energy is put in, or does the system release excess energy to break old bonds? The system has got to absorb energy in order to break those old bonds. To break old bonds, the system must absorb energy. So the system increases its energy content because energy has got to go in to break those bonds. What happens whenever new bonds are formed? Well, remember, why do bonds form in the first place? So that systems can become stable, so that systems can reach a lower potential energy state. So what happens energetically whenever new bonds are formed? Energy is released. So every single chemical reaction will involve these two energetic processes: the addition of energy to break old bonds, and the removal of energy flowing out when new bonds are formed. Old bonds get broken, that requires an input of energy. New bonds are formed, the system reaches a lower potential energy state, therefore energy gets released. So there's a positive energy change and a negative energy change. So we can take those energy changes and combine them to get the overall energy change of the entire reaction, given right here. The energy change of the reaction is equal to, very simply, the sum of these energy changes. How much energy had to go in to break the old bonds, minus how much energy had to come out to form the new bonds. And there are basically two different scenarios. It can either take more energy to break old bonds compared with the amount of energy that comes out to form the new bonds, or vice versa. Here's an example. Imagine that this reaction, I had to put, do you remember the unit used, by the way, to measure energy? It's joules. So let's imagine that I had to put 10 joules of energy in to break these old bonds. But whenever the new bonds formed, I only got 2 joules of energy out. So what is the overall change? let's say 8. I only got 8 joules of energy out. So what is the overall energy change of the entire reaction? Which is 2, positive 2. What does that mean? That means that overall, for this reaction to occur, 2 joules of energy must be added. 2 more joules of energy are required to break the bonds compared to the amount of energy released when the new bonds form. We call that scenario an endothermic scenario. Overall, the system absorbed more energy than it released. Positive delta E. The system must gain more energy to break the old bonds compared to the amount of energy it lost to form the new ones. The energy change of the reaction is positive. Positive delta E, we call that endothermic. The system had to absorb more energy than it released. Now, where does that energy come from? It comes from the surroundings, and it will always flow into the system as thermal energy. So thermal energy basically gets sucked in from the surroundings, and therefore the surroundings would actually become colder. These are things that you must know about an endothermic reaction. An endothermic reaction, the system has absorbed energy overall from the surroundings. Therefore, the surroundings get colder. It took more energy in to break the old bonds compared to forming the new bonds. Now let's imagine a scenario where the reverse is true. And this is actually accurate for this reaction. Let's say that the amount of energy required to break these old bonds, the amount of energy that must get sucked in from the surroundings, absorbed from the surroundings, the amount of energy the system must gain to break the old bonds is 8 joules. But the amount of energy the system loses when the new bonds get formed was 10 joules. Now what is the overall energy change of the whole reaction? 8 joules of energy in, 2 joules of energy out, negative 2 joules. That is known as exothermic, a negative overall delta E, a negative overall change in energy. More energy was released than came in. Overall, the system releases more energy than it absorbed. And how does that energy interact with the surroundings? It flows out to the surroundings as thermal energy. So what's going to happen to the surroundings? The surroundings are going to get hotter. And often, in very exothermic reactions, the surroundings get so hot that all the extra energy gets released as light and heat in the form of fire or an explosion. That's what's happening here. Whenever hydrogen gas and oxygen gas react, it is very violent and dramatic, and a lot of extra energy is released in the form of light and heat and sound. Exothermic reactions may sometimes be very violent and dramatic. If the amount of energy required to break the old bonds is more than the energy to form the new bonds, energy must flow in to the system from the surroundings, so the surroundings lose energy, they become colder. However, if the opposite is true, if more energy comes out from the system into the surroundings, then the surroundings will become hotter. Endothermic versus exothermic. These prefixes, by the way, make sense. What does endo mean? It means inside. Energy is overall flowing inside the system. There's a positive delta E. My system experiences an increase in energy. It took more energy in to break those old bonds. Exo, what does exo mean? It means outside. The system releases energy. There's a negative delta E. The system loses more energy than it gained. Just like in this example, it only gained 8 joules, but it lost 10 joules. Overall, we have a negative number when we combine those. Negative delta E. Exo means out, energy is flowing out. Please, please, please remember that in an endothermic and exothermic, in any type of reaction, both these things are happening. It cannot be a chemical reaction unless we have both energy going in and energy coming out. It's just that one of those will win the day, so to speak, and that determines if a reaction is endothermic or exothermic. Here is a way of modeling energy or enthalpy changes of a chemical system exactly as I've just described. H2 and O2 react to form H2O. The first thing that has got to happen is energy has got to go in to break apart old bonds. Do you see how that's shown on the graph? Yeah, it's right here, this little bump or this hill. Here is where the reactants begin. The reactants begin with a certain amount of enthalpy, which is also known as chemical potential energy. So they're beginning with a certain amount of potential energy, and energy has to come in to break those old bonds. So for a moment, the energy of the system increases. That amount of energy is called the activation energy. Any and every reaction will have activation energy, the energy that has to come in to break the old bonds apart. Once the old bonds are broken, then the new bonds may form, and that is going to cause a decrease in energy. So here you can see the graph goes down. So energy comes in as activation energy, and then the system loses energy, and the products end up with some amount of energy. So here's my question for you. From this graph, can you tell me, was this reaction an exothermic reaction or was it an endothermic? The answer is that this is an exothermic reaction. And here's how we can tell. The products end up at a lower energy state compared to the reactants. So overall, from beginning to end, there was a decrease in energy. That's the definition of exothermic. The system has experienced an overall decrease in energy. Yes, it's true, the system did have to increase its energy first, activation energy, to break those old bonds. But then there was an even bigger decrease in energy. All that extra energy went out of the system. It's exothermic. What's going to happen to the surroundings? They're going to get hotter because more energy left the system, flowed out into the surroundings. The surroundings get hotter. Here are two graphs showing, as the reaction progresses, the potential energy of the system. Can you tell me which system is endothermic and which system is exothermic? This graph over here represents an exothermic chemical reaction. How do I know that? Because compare the energy of the reactants compared to the energy of the products. The whole system ends with less energy than it started with. Yes, I do have to add energy in to break the old bonds. That's activation energy. But then I get even more energy out. So there's been an overall release in energy. It's exothermic. This, however, is what the graph of an endothermic reaction would look like. We add energy to break the old bonds. Energy decreases, energy leaves when new bonds are formed. But notice the products end up with more energy than the reactants had. So overall, energy has had to increase. Endothermic, positive delta E. Exothermic was negative delta E. Overall, both processes involve positive and negative changes. Energy has got to increase to break old bonds. In this case, the amount of energy that was added is not as much as how much energy was given off when the new bonds formed. So overall, there was a net release of energy, exothermic. Here, energy was added to break the old bonds, but then not that much energy was released when the new bonds were formed. So overall, the energy change is positive. Endothermic versus exothermic. Which one is going to make the surroundings colder? Endothermic, because where did that energy come from? How did the system end up with more energy? It had to suck it in from the surroundings, so the surroundings get colder. Exothermic causes the surroundings to get warmer because there's a net release of energy out into the surroundings.